Good afternoon. Take a look at the input file that we generated yesterday, and so the first script that we just generated yesterday was a very simple script just to highlight the various commands. Okay, and like I mentioned, this if you look at the dump file and load it onto Ovito, you might not see the atoms moving and reflect the fact that or reflect any temperature for that particular system. Okay, so what is basically happening is that it's not enough if you just give the initial conditions and the initial positions. You are supposed to integrate the equations of motion so that the coordinates of each and every particle and the velocities of each and every particle are actually updated with time. Okay, so we will now generate a slightly different version of the input file, which is very similar to the previous one, except that now what I am going to do is, after initializing the temperature to a set value, say 300 Kelvin, and I am going to start integrating the equations of motion. Okay. For integrating the equations of motion, you use what are referred to as fixes in LAMMPS. There are different kinds of fixes, each of which is meant for a different purpose. The simplest one is obviously an NVE integrator. So you are having a system, you are having a set of initial positions and initial velocities, and now you are going to, that means what does it mean? It means that the initial energy, total energy of the system has been set, right? And with that position, you are going to start evolving the positions and the velocities of all the atoms in the system. So this is the input file. It is pretty much the same until here, where I say velocity all create 300 Kelvin. This is a random seed. I want a Gaussian distribution and I want to cancel out any rigid body translation and rigid body rotation. Then I say fix 1 all NV, which means this is actually the idea of the fix which we want to refer to later on in the script. This is the set of atoms or the group to which we want to apply the fix or perform the integration. So as you can see, you can actually not necessarily have all the atoms in a particular fix that you are using. So for example, you could have a system and only the surrounding, you could choose a surrounding shell of atoms in the simulation box and apply a different fix to that, and apply a different fix to the set of atoms that's present within that shell. Okay, all that is possible, but in this case we are actually applying the fix to the entire set of atoms, all the atoms here. And during the process of integration, I want to dump once again the positions and the velocities of all the atoms in the system, and I want to do it every 100 steps, and I want to do it in a file called trj.dump. Okay, one of the things you should notice is that when you use a specific ID, for example, earlier on in the same file I had used a dump command which looks like this, right? This is just to print the initial configuration of the system. I had used exactly the same dump ID. Okay, now if I want to use the same dump ID, I need to undump it, stop the program from writing out information into that file, and then it allows me to use the same dump ID. Okay, if I did not do this, if I said dump here and again used dump underscore 1, then it would throw up an error saying that this thing has already been used, and it is going to happen only when it reaches this line. So you need to make sure that you are not using the same dump IDs or any IDs. For example, even the fix ID, you should not use one until and unless you have actually unfixed it, stopped performing that integration process. Okay, so this fix command basically performs a NVE integration, updates the equations of motion, updates the positions and the velocities like I mentioned, and as it is doing so, it is going to print out the thermodynamic information every 10 steps and dumps the coordinates and the velocities every 100 steps. Now this is run for about 10,000 steps. So 10,000 steps means 10,000 multiplied by 0.001, which results in about 10 picoseconds of simulation. Okay, and that's only about 4,000 atoms. So this takes a little bit of time to run. So so if you want to see how it runs, we can. So let me run it for just 1 picosecond. It's done. So when you look at the log file, some additional information is also available. It kind of tells you how long this simulation has actually taken to run, and this is useful for you to decide loop time of 11.3296 on one processor for 1000 steps with 4000 atoms. So this is the total number of seconds it has taken to run on this computer. Okay, and this is going to be a very important information for you to decide, how long or estimate how long your simulation is going to run. Okay. You should also remember that a molecular dynamic simulation does not take time only to simply run, but every time you are asking it to output data, also it is going to consume some time. So if you are going to ask it to dump the positions and the velocities of 1,000,000 atoms every step, then that input output operation is going to consume time. So that is also an important thing for you to keep in mind while you are setting up your simulations. Okay, so what did we do now? We set the temperature to about 300 Kelvin. That means we have initialized the velocities of all the systems. We have all the atoms sitting in their equilibrium positions. Okay, and then we have set the velocities of all the atoms to reflect the 300 Kelvin, and then we have started integrating the equations of motion. Okay. So the question now is, what does the temperature turn out to be? What does the pressure turn out to be? And what is the energy of the system? These are some of the things that we can look at. Okay. The first thing is, let us look at the temperature. So I have already finished these calculations. I have done it for a longer period of time just for illustration purposes. So I won't run it again here for that long time. So this is the temperature profile. So what are you seeing here? You initialize the temperature at 300 Kelvin. So the first point is at 300 Kelvin, right? But as the simulation began to evolve, you started reaching some other temperature, and it happens to be half of what you started off with, right? Close to half of what you started off with, right? You can experiment this with many different temperatures. For example, if you set the initial temperature to be 500 Kelvin, it will, and if you did exactly this, it will converge to 250 Kelvin. If you started off with 450 Kelvin, it will converge to 225 Kelvin. Okay, so the set temperature is actually not the temperature that it reaches to under equilibrium conditions. Okay. The reasons, there are a very rigorous derivation which can be shown as to why this is taking place. So especially for systems where the interaction between the atoms is governed by a harmonic potential. Harmonic potential means just a linear spring. Okay, you can actually show that using a rigorous derivation, that the set temperature is actually twice the temperature that it reaches at equilibrium. Okay. Even for systems which do not have these, where the interaction potential is not harmonic, if the atoms are going to be vibrating about their mean positions very little, okay, even though the interatomic potential may be something as complicated as the Lennard-Jones, within the vicinity of equilibrium, it's almost harmonic, right? So even then, you will be able to see the set temperature being twice that of the temperature that it reaches equilibrium. So what do you think is the main reason for this? Why does this happen? Why should it be half? What happens? Correct. Yeah, so initially initialized only the kinetic energy part of the system, right? You didn't do anything to the potential energy part of the system. So when all the energy that was given to it was kinetic energy, as the system evolves, the energy is being distributed between the kinetic energy part and the potential energy part. Consequently, the temperature at which the equilibrium temperature to which it reaches is less than the temperature at which you set. Okay, and because this is almost harmonic, it happens to be T set divided, the equilibrium temperature happens to be T set divided by 2. So if you want a system to be equilibrated at 300 Kelvin, just by initializing the velocity to 300 Kelvin, it is actually not sufficient. Okay, and for more complicated systems, your temperature may not necessarily oscillate about T by 2. So you will have to do something in order to set the temperature of the system and bring it up to the required temperature that you need. Okay, that's basically that's where we talk about velocity rescaling or using thermostats in order to rescale the temperature of the system. Okay, so the pressure of the system is about 70,000. So if you take a look at the log file, so this is step, time, temperature, potential energy, kinetic energy, total energy, pressure, volume. So pressure is this, so which is this, and it converges to some 7525, which is in terms of bar. So I have just divided it by 1000 and plotted it in terms of thousands of atmospheres, and that's what you are seeing there. Okay, that is the pressure. Okay, and the volume is obviously fixed, and it will be exactly what you started off with, because you are not allowing the volume of the system to change. This is in fact NVE integration, right? If you look at the energy, so this is the energy distribution. So you started off with, this is the potential energy part, this is the kinetic energy part. Okay, this is what you gave initially, and then it has redistributed itself between the various degrees of freedom that's available to the system. However, the total energy of the system is perfectly a constant, because you are obviously just the initial kinetic energy that you gave by setting the velocities to 300 Kelvin is actually the total, governs the total energy of the system. So that is what it is going to be. After that, the energies are being distributed between the potential and the kinetic energies, and you have something that looks like this. So there is a little bit more statistical mechanics that one can do in order to understand why the energies are being distributed in a particular manner, and also for the the reason as to why the final equilibrium temperature turns out to be T set divided by 2. Okay, so if possible, I will just post the derivation in the notes that I am sharing with you. It should be clear from that. Okay, so are there any questions in this? So now let us take a look at our trajectory and see if, so you can see some movement in contrast to what you saw yesterday, where the atoms were not moving at all. Okay, so this is essentially because now the atoms are being integrated and you are getting new positions and velocities for all these atoms, and they are jiggling about their mean positions. Okay, so this is how you can start to visualize your MD simulations using OV2. You just have to drag that particular file, dump file, into this window, and it will open up. Are there any specific questions regarding this? So after I ran it for about 1000 steps, I am stopping the process of writing out information into the dump file, and I am also performing an unfix. That means I am going to stop initializing that command. Okay, unfix 1. Okay, you can have any arbitrary names for the fix ID, and I am unfixing it once I am done with the simulations. So let us take a look at the LAMMPS documentation to see other types of fixes which may be present. So what we saw here was fix NVE command. It's a basic integrator, okay, and you can have different types, but this is what we most commonly use. So it's just fix, there is ID for the fix, the corresponding group ID, and followed by NVE is what you need in order to run this. But this is just going to perform a simple integration, there is nothing more to it. But if you want to now bring the system to a specific temperature, okay, then you need to couple the existing temperature to some sort of an external bath, and that bath will actually is supposed to constantly pump in heat to the system so as to raise its temperature to the required value. Okay. This process is referred to as a thermostat. So you have a thermostat, Nuse-Hoover thermostat as we call it, and that is done by using what is referred to as the NVT command, fix NVT command. Okay, again same, so fix ID, okay, the group ID, there is a set of all atoms for which you want to apply this fix, the style name, so which can be NVT or NPT or NPH. Okay, so in NVT the only thing that you want to control is the temperature, whereas in NPT you can control or specify the particular value of pressure and temperature that you want the system to reach. And in NPH it's a combination of pressure and enthalpy. Isenthalpic ensembles can also be realized. So depending upon what you are using, whether you are using NVT or NPT or NPH, the keyword and the corresponding values that you have to give can actually be quite different. So enthalpy, isenthalpic. So if you have, so let me open that, let me see if I have a, so in this case what I do, almost everything is the same. Okay, I provide an initial velocity, okay, and I print out some information here. Now I want to change the temperature slowly and the pressure slowly. Okay, so fix to all, I use NPT, I change the temperature from, you remember when we just created all the, when we just created the velocities corresponding to 300 Kelvin and ran the NVE simulation. So this is actually going to result in ending the temperature at around 150 Kelvin. So now I want to perform an exercise where I slowly ramp up the temperature from 150 Kelvin to actually 300 Kelvin. So fix to all NPT, and I say that my start temperature is 150 Kelvin and I want to end at 300 Kelvin, and I specify a parameter called as T damp, and then I specify ISO, which means I want to isometrically apply the pressure, which means the pressure is going to be the same in all the directions, and the starting value was 70,000 and I want to bring it down to 1 bar. It was 70,000 bar previously, but now I want to bring it down to 1 bar. So I want to bring it down to say atmospheric conditions, 300 Kelvin and 1 bar atmospheric pressure. Okay, and I have to specify something called as the P damp. We will come to what this P damp in a little bit, but let us first see what are the results of this simulation. Okay, and I run this again to about 10,000 steps. I unfix it and then perform once again an NVE simulation. So if I ran that simulation, so this is what is going to happen. So the first set that you are seeing here is for the NVE part, where the temperature was just set to 300 Kelvin and then it came down to 150 Kelvin. Okay, and then this is the part of the NPT where I am slowly ramping the temperature from 150 Kelvin to 300 Kelvin over 10 picoseconds. Okay. However, after that I ran a NVE. Okay, why did I run the NVE? NPT is what? NPT or NBT, either of them are essentially involving the system exchanging heat or some sort of work with the environment so as to bring up the pressure and the temperature to the required value, right? Now I am doing this for some time. I am continuously pumping in heat or removing heat or doing some mechanical work on the system by resizing the boxes so as to reach the required temperature or the pressure. Okay, I am doing it for some finite time. So in this case it is 10 picoseconds. But after that, I don't know if at the end of the 10th picosecond, the system has actually reached equilibrium, right? So what is the definition of equilibrium? What is the definition of equilibrium? When has something reached thermodynamic equilibrium? How will I find out?
So, means when the thermodynamic parameters of temperature, pressure and chemical potential do not change with time and are same throughout the system, then it has reached thermodynamic equilibrium.
Okay. So now if I have a rod, okay, the temperature on the left hand is say 300 Kelvin, the temperature on the right hand is 500 Kelvin. After it has reached steady state, okay, the temperature at any single point never varies with time.
But still it is not equilibrium.
But still it is not an equilibrium state, right?
No, it is not an equilibrium state because temperature is not same throughout the system.
The temperature is not same throughout the system. Okay. Another way of looking at it is, but how will you actually find out if the system is in equilibrium? The only way to find out is to isolate the system from the surroundings, right? You take the system and isolate it from its surroundings. If after isolating from its surroundings, nothing inside changes, then the system is said to have reached equilibrium, is said to have been in equilibrium with its surroundings, isn't it? If you have a body and it's at constant temperature, then if you isolate it from the surroundings and then look at the temperature, it would be the same if it was actually in equilibrium with the surroundings. This bar, which was having different temperature on either sides, if I take it and isolate it from the surroundings, immediately the temperature will start changing inside, because there will be heat flow in order to make the temperature uniform throughout the system, right? So the manner in which equilibrium is checked is by isolating the system from the surroundings. So that is exactly what I am doing here. So after having this NPT fix for some time and allowing the system to exchange heat or mechanical work with the surroundings, I am stopping that fix and starting a NVE, and this NVE is actually an isolated system, and I am checking if the temperature and the pressure are what I want. Now it so happens that when I stopped it and ran the NVE simulation, the temperature was a little bit lower. It was somewhere around 250 and it has not yet reached the 300 Kelvin value that I wanted. Okay, it has not reached the 300 Kelvin that I wanted, but it has reached some other value. Why is?
Because you program it to run till 300.
Yeah, but what is happening is, so it is constantly pumping in some energy, but the time for which I have done it is not sufficient enough for it to actually reach that temperature.
So if you increase the number of iterations with the same command,
It will.
like this is the command, like say pressure is 1 bar and the temperature is more than 300, break the iterations even if you give more iterations. Say,
No, that's not what I have done.
Yeah, you did run it till 10 because
Yes.
irrespective of the temperature or pressure.
Correct.
So if I say I run it for 20,000 iterations and if I mention the same command, will it break out when the temperature?
It will not break out. It will run. It will keep running it. It will not break out unless you explicitly tell it to break out. It is going to run for as many time steps that you have specified here. So let us take a look at that input script once again. So yes, or it should continue to pump heat so as to maintain that temperature.
Can we input a heating rate?
No, you can't. When you specify the temperatures, it is going to do it. The rate, well, you can. That is what the T damp and the P damp do. So I don't know whether I have examples for that in today's class, but let me take a look. So let's take a look at the input file before we answer that question. So in the npt command basically took a couple of different, it took this tdamp, okay, which kinds of tells it how fast you want the temperature to actually reach the value that you require, and pdamp is actually how fast you want the pressure to actually reach the value that you require. Two high values essentially means that you are forcing the pressure to come to the value that you require very quickly, and you will see huge fluctuations in the pressure. And if you give too low a value, then it will take a very long time for it to actually reach the pressure that you are requesting. Okay, so usually there is a thumb rule that one uses when you are using these NVT and NPT commands. So here a Nuse-Hoover thermostat will not work for arbitrary values of tdamp. Okay, so usually a good choice for tdamp is around 100 time steps. So our time step was 0.001, so that's the reason why I have given 0.1 there. Okay, and for similarly for pdamp it is about 1000 times the time step, which is about 1. So that's why you see a value of pdamp to be equal to 1, which is the standard way of, which is the LAMP's suggested way of giving the values for tdamp and pdamp. Again, what exactly tdamp and pdamp are doing to the equations of motion is not something that we are going to be teaching here. Okay, so that involves actually coupling the system to an external bath and solving the equations of motion along with some additional degree of freedom. This tdamp and pdamp are going to control how quickly the requested temperature and the required temperature are going to match. Okay, so I have, after running this NPT, I actually stopped it and only then ran the NV. So a good way to actually check if your system has reached equilibrium is actually to, after performing the NPT or NVT, whatever you want, stop that fix by doing this unfix command and check all the parameters if they have reached the value that you requested. So I don't know what the pressure value reaches. So pressure value is this. So you see it was 70 and then it has come down and it has reached some specific value. I really don't know if it is 1, but it's possible that it is 1. It's not really 1 yet. Yeah. So that's the way you check if your system has reached equilibrium. And this is the way the energy basically varies. So initially this is the part where you do a pure NV initially. So this is the total energy, this is the potential, this is the kinetic energy, and then you are slowly increasing the temperature. So the kinetic energy increases and the potential energy is decreasing. You are decreasing the pressure of the system from huge value, and then after 10 picoseconds you have stopped doing anything and again running NV. So you see the kinetic energy being constant, almost constant, the potential energy being almost constant, and total energy being almost constant. So during this period, because you ran NPT, you are expecting one thing, you are expecting the simulation box to actually become huge, because what have you done? You have decreased the pressure from 70,000 bar to have a pressure of only about 1 bar, right? So let us take a look. If you saw that, did you see the box actually increase in size?
Due to the decrease in pressure.
Yes. So when you do NVT alone, the volume is held fixed, the temperature, only the heat input is given. When you do NPT, you are controlling both the temperature as well as the pressure. Consequently, to have the right pressure that you want, the volume of the entire simulation cell will be adjusted. Okay.
In NVT simulation, N, V and D are remaining constant.
Yes.
N is the number of atoms, right?
Yeah.
In NPT simulation, N is constant, but pressure and temperature are changing.
Okay. They are not changing. That's a good point. So in NPT, actually what you mentioned is right. The statistical mechanically, the pressure and the temperature of the ensemble is fixed. That is the macro state. Okay, but what you are trying to do in molecular dynamic simulation is you don't really know the positions and the velocities or the equilibrium configurations that the system must have at that pressure and temperature, right? You don't know how the velocities should evolve or how the position should evolve. So what you are doing is you are starting off with some arbitrary state and using this NPT fix to actually kind of training the system to reach that pressure and temperature. So here the use of NPT is not exactly fixing the pressure or fixing the temperature. It involves changing the pressure and changing the temperature to some fixed value. Hopefully, if you have done it long enough time, your pressure and temperatures will reach the value that you have requested.
So the final values specified are the ones where I want it to equilibrate.
Where you want to equilibrate to which you want the system to equilibrate to.
And in NVT simulation, N and V are fixed.
Fixed.
But I want the T to equilibrate at the
That value. That is right. So this is more like,
The ramp part is not important.
the ramp part is not important. You can start off and end with the same value. So these are given for different reasons. So if you want to do any specific temperature rate and all that, then you can do that. Okay. Usually we start off at the same temperature and in the same temperature, and it will equilibrate to that particular temperature if you have trained it or if you have given enough time steps for it to work.
Sir, for real objects, like if I'm having a piece of iron in this room, that pressure on that piece is 1 atmosphere because that is the pressure exerted by the atmosphere on that piece of iron. But in a molecular dynamic simulation, the simulation box which we are defining, it is being repeated in all 3 directions, right? Because of periodic boundary conditions.
Correct.
And the pressure which is being calculated by the core, because of the running of the core, that is the pressure experienced by.
It is the pressure exerted by the molecules on a container of the size of the simulation box.
The pressure exerted by the molecules
On the size, that is the definition of pressure, right? What is pressure actually? If you talk about, let us talk about the pressure of an ideal gas inside a container.
Yeah.
What is meant by pressure?
The pressure exerted
By the molecules on the force which they hit the surfaces of the molecules is what is constituting the pressure. So that is this is that pressure. Okay. Any other questions? So now you can go back. I will upload this, and you can play with it a little bit and try to see if you are able to show PV is equal to yes.
So when we talk about equilibrium, do you mean that every single particle in the box has the same energy, or?
No. At equilibrium, no, it need not have the same energy. No.
Like, what exactly do we mean by the properties do not change with space?
The particles have, the velocities of the particles are for example, if you are talking about an ideal gas, then at equilibrium the velocities of all the particles should be such that they have the Boltzmann's distribution, right? So equilibrium property is for the entire system, the bunch of the entire atoms. It is not for each atom. In fact, we saw in statistical mechanics that it is in fact not the same for all particles.
So when the system reaches thermodynamic equilibrium, means that happens when thermal equilibrium, mechanical equilibrium and chemical equilibrium are individually reached.
Yes.
So chemical equilibrium is reached when chemical potential is same throughout the system and does not change with time.
Yeah.
Thermal equilibrium is reached when temperature remains same throughout the system and does not change with time. And mechanical equilibrium means pressure remains same throughout the system and does not change with time. So if the temperature is remaining same throughout the system, it simply means that the average kinetic energy is not changing as we go
Correct.
from one part to another. But the individual particles may have different kinetic energy.
That's what I am saying. Yes, it need not be the same. It's only the average. The equilibrium is defined only for the average, for the entire system. So now will you be able to run some simple simulations for equilibrium? Would you like to start trying something? Shall I give you some exercises from next class onwards? Okay. So we'll stop with this today and we'll continue in next class.